Hello everyone, my name is Łukasz Sztukiewicz, and this summer I worked in the Auto Lab under supervision of Jack Good and Artur Dubravsky. Our research topic is called Learning Decision Trees when you cannot trust your labels. In recent years, machine learning has proven its usefulness with wide adoption in various applied domains, ranging from efficiency-oriented finance to human-centered medicine. However, there is no machine learning without data. Interestingly, despite significant advancements in research on data modalities such as text, images, and videos, tabular data is still the most commonly used data modality in practice. As a result, many techniques have been proposed to learn from tabular data, with decision tree-based methods proving to be the most powerful, especially in the time series domains, even in the light of the recent advances in deep learning. The roots of decision tree techniques date back to early approaches such as Quailian ID3, followed by developments such as C4.5 and classification and regression trees. It is well known that these algorithms are naturally unstable, meaning that slight changes in the input data can produce very different output models. Therefore, ensemble methods emerged to overcome the instability issue and improve the performance further, evolving to the current state-of-the-art industrial implementations, with notable examples such as XGBoost, Microsoft's LightGBM, and Yandex CutBoost. It is essential to recognize that while these algorithms address common data issues like missing values, outliers, and feature noise, they are developed with the assumption that the target variable is correct. As a result, the reliability of the data annotation is often overlooked, and in reality, labels are rarely perfect. The problem is evident in the recent estimates that the even databases commonly used in research contain up to 10% label corruptions. This challenge has recently drawn the attention of the deep learning community, but despite the interest, work on interpretable machine learning methods like decision trees is very limited. The approaches to deal with label noise in data can be divided into database techniques that modify the underlying dataset and algorithm-based techniques that aim to make use of the full data, even if noisy. The most common database technique is to filter the potential noisy samples. However, this approach is criticized for eliminating too many useful instances. On the other hand, the algorithm-based techniques aim to make use of the full unmodified dataset and solve the problem by various modifications to the learning algorithms. The most common ones are symmetric loss functions and loss correction. However, in our work we prove that these approaches are not useful for decision tree induction. In particular, correcting loss function results in the fact that the corrected tree structure does not differ from the structure built from a clean dataset. On the other hand, when we try to use symmetric loss functions, the potential splits lead to both children nodes having identical leaf values, resulting in the zero gain and therefore too fast pruning, which result in high underfitting. That's why there is a need of different approaches for learning decision trees on data with label noise. Our proposed methods combine the research of fuzzy decision trees, robust splitting criteria, and feature transformation learning. In particular, our approach is based on kernel density decision trees, recently proposed fuzzy decision tree algorithm. This approach has two main strengths. The fuzzification natively represents the uncertainty in the tree structure, and secondly, the usage of kernel functions smooth and increase merging of decision boundaries. Moreover, we use imprecise info gain, a robust splitting criterion that takes into account the unreliability of the data during decision tree induction. Ultimately, we also use feature transformation learning to learn features that are easy to discriminate by decision trees. This optimization leads to obtaining small performance trees. The characteristic of our approach can be nicely demonstrated on this visual, where we show a comparison of decision boundaries of selected models under 20% uniform noise. First, we compare the performance of decision boundaries of models trained on the clean dataset. Then in the second row, we show the same models, but trained on the noisy data. This toy example shows that our approach results in better, smooth, high-margin decision boundaries. We comprehensively evaluate our approach on 5 popular benchmarking datasets. The robustness is measured by expected loss of accuracy with respect to the model trained on clean data. In this table, we report the score and the standard deviation averaged across 4 noise ratios. Then we evaluate the predictive performance of our models with weighted F1 score calculated with relation to the standard decision tree performance. Our research communicates that we can learn single, robust performance trees even on data with high label noise ratios. I would like to thank my mentors, Jack Booth and Artur Dubravsky, for constant guidance and support, and RISC program directors, Rachel Bursin and John Dolan, for making this research experience possible. Thank you.